why is insulation so important? So, as Gary said, it makes up a huge volume in the building, and actually it is one of the single most influential materials within the building. So it affects the properties of the building, the comfort that people feel in the building, it affects their enjoyment of the building, the want to be in that space, and along with that it affects people's psychology and their health as well. But equally, because it is so influential, we can actually use the properties of that insulation to tailor the inside of the building, to give it properties that make it very stable in there, that make it a very, very enjoyable space to be in. So now I'm going to talk about dogs. No, not really. What did I do then? So I'm going to talk about comfort. We want to be in buildings that stay at an even temperature, that buildings that aren't ragingly hot one minute, that aren't freezing cold the next minute, that don't have howling gales blowing through them from an air conditioning unit running, that don't have big heaters blaring away, creating big convection currents in the building. We like nice passive environments that stay at a nice even temperature. Lightweight insulation gives you very low thermal conductivity, and that's great. You know, we can get some very, very good U values with very, very thin insulation materials. But because they are extremely lightweight, they achieve their equilibrium state. So the point at which the amount of heat going in is at a steady state, and the amount of heat coming out of that insulation is at a steady state, and they achieve that really, really quickly, which can be useful in certain types of building, but in buildings that are occupied a lot, it's generally less useful. So high density materials, and particularly natural fiber materials, tend to have a very high specific heat capacity, which means it takes actually quite a lot of energy to change the temperature of that material by just 1 degree. And consequently, it takes a long time for them to reach that equilibrium state where the amount of heat going into the wall reaches a steady state. Again, the heat coming through the other side reaches a steady state. Now, heat currently kills around 2,000 people a year. This is a global figure, a European figure, rising to around about 7,000 people a year over the next few decades. So, sorry, I think that's a UK figure actually, sorry, ignore that. It's been a while since I did this one. This is a UK figure, so we're expecting 7,000 people to die each year in 20 years' time from overheating buildings. So it is absolutely vital that we build buildings that stay at a comfortable, safe temperature very, very easily without having to use a lot of energy to keep them at that point. Wood fibre and natural fibres, as I say, have this huge what's called a decrement delay. So it takes a long time for that heat to transfer through the walls, and it takes a long time for the heat that's penetrating the fabric to actually have an effect on the building, and that helps passively regulate the internal environment. So we can build buildings that don't need big systems in them to regulate them, which obviously has a big impact on energy usage. Now, part of the reason for this is that natural fibres, wood fibre, are very complex materials. They're not just doing one thing. Synthetic fibres tend to be designed to do a job, and they are designed to do one job. So wood fibre or natural fibres, as Mark's been talking about, absorb and desorb water, and actually that changes their properties hugely as well. It changes the heat capacity of those materials as well. And so there is also a very useful function when you're using natural fibres up against the inside of masonry. There's actually a phase change process which is going on, which improves the performance of those wood fibres by anything up to about 25% over and above what you'd expect just by looking at their thermal conductivity. So moisture itself actually varies and can improve the thermal properties of these materials. Looking at okay, this is my own house, which is why I've got figures for it, so bear with me. This is the red squiggly line are the external temperatures, so they are varying between minus nearly -5 at one point, up to about 27, 28 degrees. There's a huge amount of variability externally, and you can see the blue line at the top there is, okay, a little bit squiggly, but essentially varying between about 22, maybe down to 21, and up to a maximum of 24. Now, there's no cooling in this building, it's important to point out. There is a small heating system in it, but there's absolutely no cooling. But using the right materials, and again, as it was my house, I thought I'd put the right materials in it. We've used a lot of natural fibre materials, we've used clay products as well, and the whole sort of portfolio combined creates a building that stays at an extremely stable temperature. So thermal performance, thermal conductivity is obviously the main measure of comparing insulation materials, but it's a bit like telling a sheep farmer in Wales that the best car that he could possibly buy would be a Bugatti Veyron because it's clearly the fastest car on the road. Not largely that useful on the hills of Wales. And so when we talk about insulation materials, as again everybody's alluding to, we need to encompass all of their properties and not just one. So looking at a long decrement delay in buildings means that, and also the combination of the build-up of the materials on the outside means that we can create buildings that store heat on the outside of the building, and overnight when the external environment cools down, that heat can be re-radiated back outwards. Thermal mass also has a big effect on overall heating and cooling by virtue of the fact that it can actually store heat during the day. So, for example, in the spring and autumn time, thermally massive materials will store sunlight that is accumulated during the day. They'll release that during the evenings and increase the warm period inside the building, so reducing the time that you actually need to heat the building. Additionally, particularly with some of the wood fibre systems, the way that they're detailed on buildings as well has a big impact on the overall U value that is required. So there's something called psi values which are used around openings, and using the wood fibre products we can actually target higher U values to give the same overall thermal performance, where using synthetic materials might require a lower U value. Now I'm going to jump slightly and show you an iPhone and a green screen. This is a bit of slightly DIY experimentation, but it gives you an idea of the thermal mass and actually the speed at which heat moves through very lightweight materials compared to more thermally massive materials. We used a polystyrene box and we used the wood fibre box. Now they both have the same U value, which is very important to say. So if you just compared U values, you'd expect them to perform in exactly the same way. However, they do vary quite a lot. So we put two boxes outside overnight, one polystyrene box, one wood fibre box. We brought them back into the room, and you can see on the top there, the internal temperature in the room was at 20.28 degrees. The polystyrene's at 5.5, the wood fibre 6.5. So 30 minutes after we brought them back into the room, the polystyrene box has risen by 8 degrees, the wood fibre box has risen by 0.8 degrees. So this, they're both in the same environment. Then, the polystyrene isn't next to a heater or something. They're both in exactly the same space. But because there is no thermal mass to the polystyrene, the heat moves through it really quite freely, even though on paper the U value is exactly the same. After an hour, the polystyrene's risen 11 degrees, the wood fiber's risen by 2 and a bit degrees. So again, you're talking about a massive difference in what you're feeling inside those boxes. So if you imagine this is a hot sunny day outside and your super low U value building is using extremely lightweight insulation, actually pretty soon after it's getting hot outside, you're cooking inside. Is this going to play? How do you make it play? Would you like to press the space bar or something? Oh, there we go. So very quickly, it's going a bit quickly, but you can see how quickly the polystyrene on number 2 there is rising up to very close to the internal temperature. Even after 4 hours, coming up to 5 hours now, the wood fibre box is still at 2.5, nearly 3 degrees, in fact 3 degrees below the internal environment. So nearly 5 hours later, there's still a big difference. So that's why just looking at U value is really a misnomer when you're actually considering overall building performance. I've got no idea how long that took, but does anyone have any questions? Hi. Sorry, say that again. Oh, there we go.
That was your experiment for warming up. Is it exactly the same for cooling down then?
Yeah, it is.
Just the opposite?
Yeah, exactly. Yeah, it is that simple.